There you go, Ken.
Yeah, sorry I'm late. I'm sorry I'm late.
Oh, that's okay. Yeah, I was wondering, there's no one in the class and there is no one online. What should I do? I have not yet taught an empty class and an empty online. That means to say just keep a recording and yeah. So I guess eventually one of these days that will happen.
Hopefully not.
Okay. So what things?
Good. Things are good.
Let me. So we have homework 6. Due Thursday. And we have midterm 2. And for now, this is in class and no Zoom. That's tentative. Hopefully, what we are seeing keeps going and things get normal by fall, if not earlier. Okay. So last time we started on an example and then we were caught up with time. So we sort of reached the very end, but I couldn't complete it. But it's a good enough example that I will go over that again. And actually also do, once we finish that problem, basically, we try to do the Lagrangian mechanics. And typically what happens is that you're given a problem and we try to write the Lagrangian for it and then write the equations of motion for it. So that's pretty much what we will do in a week or two, or for about a week or two. And I remember the examples I've done in the class last time was the opposite. I wrote down the equations of motion and tried to get the Lagrangian, but we want to do the opposite very soon. So I'll do one example that went incomplete last time. I'll complete that and then reverse the exercise and start getting the equations from the Lagrangian. So, let's call what we are doing Lagrangian mechanics. I'm not sure whether that's what it's called. Lagrangian mechanics. Newtonian mechanics. So instead of starting from Newton's equation, we start from the Lagrangian. So the idea we set was that given any system, we had to first try to write the Lagrangian. So first we say there is a Lagrangian. Okay, so that's a function of the position of the particle. So this is x or r. This is x as a function of time. Then we have derivative of x as a function of time. This is vector now. This is also a function of time. So this often I will start using the letter velocity as a function of time. Notice that the velocity, the way we have defined it here, it's a dependent quantity. Once you know the position, taking the derivative gives us the velocity. and then that's time. Also could be. Often, many of the examples that we do, we don't have the time dependence, but that's good to know the difference between, at least we will do few examples where there is time dependence and where there is not. And at least at a very general level, we will state what that means. That it is important because later we will talk about Hamiltonian, and the Hamiltonian can be interpreted as an energy only when there is no explicit time dependence in it. Once we have the Lagrangian, we say the action is defined as, I think I use the letter W, and this action is a functional of the vector x. What is we have talked about one variable. This vector x is just a generalization into three variables, x, y, and z. And t is a dependent quantity, which is what it is integrated on. So you go from t1 to t2, dt, and the Lagrangian. And stationary, so first we have Lagrangian, then we have action, then we say there's a stationary action principle.
Oh, hello. I actually forgot about the class.
Oh, sure, you're there. Yeah.
Yeah.
Yeah, we just barely began. Yeah, thank you. Yeah. Yeah, so we I was trying to summarize what we did last time. So,
Okay.
so we said there is a Lagrangian which depends on position x, velocity, which is derivative of x. In that sense, it's dependent quantity and explicit dependent in time. Action is the integral of the Lagrangian, and the stationary action principle, which often, especially in the slightly older literature, is simply called the Hamilton's principle. Like this is like Fermat's theorem. Means when we were doing optics, instead of talking about the minimization of the time taken, we say it's Fermat's theorem. So similarly here, often it's called Hamilton's principle. This is different from the Hamiltonian mechanics we will talk about very soon, obviously. That says that the action, variation in the action for the actual part of the system is equal to 0. So we say this is x and x as a function of time. Right? That's equal to 0. Notice the Lagrangian in general, especially when it becomes a more broader context, it can depend on various parameters also. For example, it might depend on a material property, or for that matter, some constant, h bar or alpha. So there are so many things it can depend on, and you can take the functional derivative with respect to all of those variables if you want to. And it is not necessary that everything the action depends on. The variation with respect to that should be 0. So there are certain parameters it is equal, the action is stationary with respect to, and those are typically called dynamical variables. So this so x will be called a dynamical variable. Dynamical doesn't mean it has to do with dynamics, but of course the context is what gives the name. There's a dynamical any variable with respect to which the action is equal to 0. The variation of the action is equal to 0 will be called a dynamical variable. And later, once this becomes a theorem, it gets reversed. You say that variation with respect to a dynamical variable will be equal to 0. You can the beginning you define it with a motivation, but then you state it as a theorem. Okay, so that's what it is. And we also said that in general, this leads to the equation. So this implies the moment you have this equal to 0, we always get time derivative of, I don't really need the parenthesis, but still, Lagrangian with respect to velocity. The velocity here is basically derivative of x with respect to time, or you can think of this as a gradient with respect to velocity, right? Gradient with respect to x is what we typically say. This is the gradient with respect to the velocity parameter, and that's equal to partial derivative of the Lagrangian with respect to position. Right? This is a vector. Notice it's L. I will also use the notation. This is gradient of L. That's a standard thing. And if you have the partial derivative with respect to velocity, it's good in that sense to say this is velocity gradient with respect to.
Dr. Sujesh, could you move the camera down a little bit?
Oh. I see. Is it? Oh,
thank you.
That's not good. Okay. Okay. So I was saying that this equation implies at a very generic level, not necessarily with respect to a certain variable, even if it is velocity dependent Lagrangian, we always get total time derivative. We differentiate between total time derivative and partial time derivative of the Lagrangian with velocity. That should be thought of as of the gradient with gradient vector, but this time with respect to the velocity of the Lagrangian. And this is the normal gradient, right? The gradient of with respect to the position. And this is often called the Euler-Lagrange equation, right? So actually, I should state that since we had the statements here. So this is Euler-Lagrange equations. And that's your summary. And we also will define the L by dV. So this will be, so that there's a definition here. I think I can, it's still visible. So we'll call canonical momentum. Will be defined as P is equal to L by dV. Right, that's here. And in that sense, you can immediately write your equation as time derivative of the canonical momentum, which is that's if it was standard mass times velocity, it is the classic force, right? Newtonian force there, and that's equal to partial derivative of L or gradient of with respect to L. Remember, in Newtonian physics, the force is equal to negative gradient of a potential energy. If you're working with conservative forces, the negative gradient of the potential energy. And we will be mostly confining ourselves to conservative forces where Lagrangian mechanics really gets useful. We will talk a little bit, very little about constrained systems and in general dissipative system, but very, very little. Okay, so that's pretty much a small, tiny summary there. And let's go over the example that we were doing last time. So we talked about a charge in a magnetic field. So we said, so example, charge in electric and magnetic field, actually, E and magnetic field B. So electric field and magnetic, in principle arbitrary. And if we write down our Lorentz force equation, we have force, and this time I want to specify what the force is. This is, we're starting from the Newtonian force, that is mass times velocity. So time derivative of mass times velocity is equal to Q times the electric field plus Q times V crossed with B. And that's your that's a Lorentz force. And the question was, the question we were addressing is that can we write the Lagrangian for this, starting from the equations of motion, that means to go in the reverse direction. What will be the Lagrangian that will give us this equations of motions if we were to use Euler-Lagrange equation. So for that purpose, we wrote this in terms of electric potential and vector potential. So we said this is d by dt, mass times velocity is equal to, this is just going over what we did last time. So electric field, remember, is a negative gradient of potential and time derivative, a negative time derivative of the vector potential, and magnetic field always is del cross A. And that's because the divergence of the magnetic field has to be equal to 0 because there are no magnetic monopoles and can be written in terms of a curl. So this is minus gradient of Q times phi. And oops, there's one more, right? Q times phi, and let me write that as minus Q dA by dt plus Q V crossed with del cross A. And next step, we expanded this vector product. So it's gradient of Q phi. And since we want to compare it with our Euler-Lagrange equations, first of all, we want to write it in the form of that Euler-Lagrange equation so that then we can identify what could be our Lagrangian if you want. So that's Q, and I want to take this to the left-hand side. Right? That's what I was doing last time. So this is time derivative, mass times velocity. Take the time derivative to the right-hand side. So that's Q times A. Now that's equal to negative gradient of Q times the vector scalar potential, and the vector product can be expanded. Notice that V is the velocity of a particle that does not depend on the gradient. So I can write this as a gradient Q times the gradient of V dotted with A. We went a little slowly last time, so look into the notes last time if you have confusions on this. Plus Q minus Q V dotted with the gradient of the vector potential. Hopefully I can squeeze that in there, but I think that's visible. Yeah, that seems to be visible. Okay, so let me take this piece also to the left. And what we did was, this is derivative mass times velocity plus, oh, I should move the camera, I suppose. that's partial derivative plus v dotted with gradient, and this is q times the vector potential. And later we identified this to be total derivative. That's where we were pretty much short of time last time. And this is gradient now. This is negative gradient of q times phi minus q times v with a. This we recognized is a total derivative in the sense that a position can depend on time itself. So vector potential A in general is a quantity that depends on position, which in turn can depend on time. So this will be time derivative of mass times velocity plus q times v dotted with q times a, I guess. Sorry, no, v dotted. Q times a, which can have x dependence in here, so that's time, and it could have time dependence also. Just to clarify that very clearly, a can have x dependence. And on the other hand, we are also saying that x does not have any velocity dependence in there. In principle, one could imagine that situation, but we don't typically have it here. So that's equal to negative gradient of q times of course, the idea is that this will become the energy, this will become the momentum, but let's go slow. If we were to compare this with the Euler-Lagrange equation, we get two things. We have momentum P. So, or let me not call this momentum yet. So the canonical momentum is the derivative of the Lagrangian with respect to the velocity. That's equal to mass times velocity plus q times a. But again, a does not depend on velocity. And the Lagrangian itself, it seems like if you were to compare the two equations, the Lagrangian itself is, or let me actually say this in two steps. So the negative gradient of the Lagrangian with respect to position, that's equal to negative q phi plus q times v dotted with a. Okay, so what can we conclude from this? What did I say? There's something wrong here. Sorry, I meant to write the gradient on the right side also. So this is negative of, so it's negative gradient of q times phi minus q times v dotted with a. Like the right hand side, I'm not saying yet that L is equal to this because I could be off by some constants, right? So here this implies, like let me begin with this one. Here, this second statement implies that the Lagrangian is exactly equal to this up to a constant. And what is that constant? That whatever that constant is cannot depend on the position, because if it depended on the position, when you're taking the gradient, that will come in. So this quantity C, let's call it C2, depends only on velocity. And it could depend on time also, because Lagrangian in general depended on position, velocity, and time. But this, whatever this piece we are missing here, that can depend only on the velocity. Similarly, if we go up here, this is a, what we are saying is that the derivative of the Lagrangian with respect to velocity is this much. So what can the Lagrangian be? We just integrate, right? If we integrate this and on the right hand side, we get the Lagrangian. So the Lagrangian could be right, up to a constant with respect to velocity this time. It can be half yeah, so this is half m v square, right? Or v dotted with v, right? Because when I take a derivative with velocity, I can hit on both the velocity and I get mass times velocity. And the second term, I can get, if it is just simply linear and velocity, so I just take a dot product with it since there are three quantities in there, so I take a dot product with that. And I am off by a constant again, so that's C1 with respect to position and time. This time, this is x. And again, remember that A depends on x, phi depends on x, so as all x dependence is spread out at various places. Together, these two equations. Oh, I was actually missing. I think I didn't move it completely, I guess. Was that clear enough? Did you guys miss things because I didn't move the board properly? Okay.
No, it's clear.
Together, we have C1 as a function of x and C2 as a function of v. Together, the Lagrangian seems to be, maybe we can write this as half mv square. And so that is this piece that is in here that you can build for your C2, and your C1 could be whatever this is. Why is there a plus and a minus off? This should be plus, correct? So there is a negative sign in there. I forgot to bring that in. We even discussed that last time. We said the plus and minus sign has to do with the fact that in charges, like charges repel and opposite charges attract. But when it comes to currents, Q times V is nothing but current, right? Charge times moving charge is like a current. So like currents attract and unlike currents repel. So that's that information about that positive and negative sign. Often this is a cause for a confusion because in another context, we also write the energy in the electric field and magnetic field is half epsilon E squared. If I were to write that here, yeah. So energy is also distributed as half epsilon E squared plus half mu naught B squared. This is also a definition of energy density. Here, it seems like the energy contained in the electric field and the energy contained in the magnetic field is of the same sign. But when it comes here, it seems like it is of the opposite sign, and that leads to some confusions. But one should remember that when we are talking about this, that is another piece in the canonical momentum. So when you take care of all this carefully, there is a complete consistency between these two relations. But we won't talk about that here in another context. That's possible to okay, so now we have the same expression here. So it is convenient to identify C1 as minus Q phi, and it seems like we can write. So this is half mv squared, and this is Q times phi minus Q times V dotted with A. And of course, now we'll be off by another constant actually. C, the way we have written is this is a constant with respect to T. But in general, we have there is an example in your homework also that a Lagrangian is not just off by a constant, any Lagrangian for that matter, there is a complete function. You can arbitrary function. You can add or subtract, and your equations of motion do not get disturbed by that at all. And that's the first problem in your homework. So so with that information there, we can just draw this. Right? We just need one Lagrangian, and that's good enough. And this will give you your equations of motion. So that's a example where you do it in the reverse way, in the sense that equations of motion are given and you try to get the Lagrangian out of it. And this is reasonably elaborate in the sense that it is velocity dependent potentials. Potential is not completely, there is an idea of canonical momentum, which is not just mass times velocity. Whenever momentum is just mass times velocity, those are simple problems. When there are velocity dependent potentials, it gets a little more involved, but very much doable, as we just know. So, from now on, at least for a few lectures, we will try to do the opposite. At least 2 lectures where we will do examples where we will explicitly state the example and then try to write the Lagrangian. That's also one needs sufficient practice to do that. So let's do a simple example where we see that, and the simplest example, or not the simplest, let's say one of the simple examples is a pendulum, right? And I try to, most of the problems that I design is around the pendulum, because I feel that is rich enough, at least in the basic mechanics kids. And it also highlights the fact that there is a constraint. So I'll talk about that. Okay, so let's talk about a simple pendulum. What does simple stand for in here? Any thoughts on that? What does simple and the simple pendulum stand for? Yeah, quiz. So let's make this a quiz. Even I don't know as such. I think it is. I'm thinking that it is when you make the small angle approximation, that becomes that's called simple harmonic motion, right? Probably that's where the simple word comes in, because we will make a small angle approximation later. And yeah, what does simple stand for? Like, that should be easy to look up. There must be clear definitions on that. Okay. Yeah, so what's a pendulum? Let's first look at the Newtonian way of doing it. So you would say this is a vertical direction, and that's your mass m. And this could be a rigid rod, massless rod, let us say, so that we have only one mass to worry about. In general, this rope has a mass, which makes it a little harder. So let's say this is massless rope or a massless rod, right, of length L. So that's your length L, and that is a mass m. And let's say this is the angle theta. And we do know that if the motion actually starts in a plane, it will keep going in a plane. Is that true? If you have a pendulum and you pull it to the right and you release it, it always goes in a plane. Is that correct statement?
I believe so.
If you release it at rest, yes, but if you give it an initial velocity in some other direction,
I don't give it an initial velocity in any other direction. I make the velocity directly point along the axis. Then what?
yes, then it'll be on a plane.
Currently not.
Really?
So that's an approximation we do. That is the idea of Foucault pendulum. Have you guys heard of that?
But
Yes.
how the directional forces are on the same plane?
Yes. Then I guess, like in the plane, in the sense that okay, so this is Foucault. I think it's right. So the point is, how do you say this? So you guys are telling me that, oh, if it is exactly in one plane to begin with, it will stay in a plane. No. Okay. What happens is that, okay, there is a plane of motion, right? If you were on the North Pole, for example, or for that matter, this was real constant uniform gravity, then surely this happens in a plane. But if, since our Earth has a spherical nature, this whole plane of motion actually rotates.
Okay, like
With respect to that.
something like the Cornelius effect. I mean, is it?
Exactly. That's correct. Yeah, that's correct. Yeah. Or this is called a parallel axis. What is it called? Parallel. Because if you go around in a circle, you don't have to come back, right? The idea of Berry phase, or what's it called? Parallel.
Not no.
Get parallel. Like if you have a vector, you go around the circle and come back, it need not be pointing in the same direction. So it's a Stokes theorem. Gives you that relation. Oh, I couldn't get that word. Parallel axis. Yeah, I forget. Yeah. So yeah, so it's just nice to know that Foucault pendulum is a generalization. So we are actually talking about the real. This is really uniform. We are not on the surface of Earth. That is constant gravity. So that's what we are. Is that clear?
Yes.
Like whatever or at least I didn't highlight it very much. But did I give enough idea there?
I remember doing a problem like this with the including the Earth's rotation.
Okay, good. Yeah, it will depend on the angle at latitude of where you are.
Mm-hmm.
So it's so what I think the interesting part is that if you're sitting on the North Pole with the pendulum, so now we are telling that okay, there is a time period of the pendulum itself, and there is a time period of the amount of time this plane takes to go around. So there is a precession angle, right? So Foucault pendulum leads to what is called precession angle or precession rate, let's say rate of precession. And if you're on the North Pole, it is exactly 24 hours. So let's say 90 degrees, right? Theta is equal to 90 degrees. That's the latitude. Then it is exactly 24 hours. And which can be imagined as Earth going around, rotating below you. Like you're standing on the North Pole, and Earth is rotating below you. But if you were on the equator, theta equal to 0, this will not rotate at all. So this will take infinite hours. Exactly on the equator, there is no precision at all. And somewhere in between, for example, on Carbondale, it will be theta is equal to 39 degrees, I think 38 to 39 degrees. And the question is, how much is this? It will surely be between 24 and infinity. So it's about probably 35 or 40 hours. And there are nice exhibits made out of this. We have one here, which is not a very accurate one, but whenever there are students visiting or high school students visiting the department, there is a temporary setup that is made where in the sand you can actually make some small small standing sticks, and this pendulum keeps striking this down, and you can actually see this within about 5 or 10 minutes. It will go about 1 degree. So it's kind of a nice effect. But let's not do that, right? So we are going to have just uniform gravity. So let's say this is uniform gravity, no other complication involved in that. If we were doing Newtonian physics, notice that what we'll do is that mg is going to be acting downwards, and there is a force of tension T that will act along the rod. And then you can ask the question, why is the force of tension along the rod? Can it be away from the rod? Can it be, what do you say? Why should it be towards the center of the point? Of course, we always do that, but if it was a rope, is it possible that if you connect the rope in a different manner, you can have the force of tension in a different direction? So remember, mass times acceleration is equal to mg plus t. That's your Newton's law. And the question is, why do we have tension right in there? Is it really necessary or not? Any comments on that? Is it possible to have? Maybe.
I think so. I think you can just switch the direction of the vector.
Direction, but then there will be a new unknown, right? Probably.
You could use the same symbol, even if it's, hello? Can you hear me?
Yes,
Oh.
yes.
I mean, you can use the same symbol, right? It's just that the T would be negative of whatever you thought it was. But anyway, that would mean that the rod is pushing, which is not really
Yeah.
what happens. Oh, it can if it's on the other side. If it's, I mean, if the mass is above the horizon or there, then yes. But yeah, I mean, we don't need to change anything in our equations. It's just the opposite direction, so it will just show up as a negative of whatever direction you have chosen.
Yeah, so you guys are telling that why this is also possible, right? They're saying this could be T. So this is an
Oh
approximate.
no, not like that. I meant only along the rod.
Oh, along the rod. Oh, along the rod, that's surely. But I'm asking the question, can this be, is this possible?
No, that's not possible.
Why not?
Well, the rod is it cannot exert forces horizontal to it because, well, forces which are perpendicular to, not horizontal. I don't know how I would say this. It does not push in that axis, in the other axis. It only pushes or pulls in one axis along the rod.
Yeah. Any other comments? Ken?
Well, I'm just thinking that if the pendulum can get out of that 2D plane, slowly but surely, like with the focal pendulum, then I guess it is possible to have some tension not along that plane exactly, right, where it is a little bit away from the rod.
I should first of all say that the focal pendulum, the motion is not due to, that's a very interesting effect in the sense it is not due to forces. That is a more dynamical thing, that because our frame is moving, so that's what happens.
Mm-hmm.
Here again, like I never addressed this very clearly before, but like if you have a rod, really, I mean, if it was completely rigid rod and And maybe yes, but typically let's ask the opposite question. What is the primary function of this force, right? Well, why do we, because that's how it connects with the Lagrangian, right? What's the purpose of this force? This is first of all, it's an adjustable force, right? What is force of tension? Like, I mean, often it can be seen as you want the Newton's equation to be valid, so you kind of, this makes sure that this is happening. It's either way. But the point is, what is the job of this? Like, in one way of looking at it is that this, if it was a rope, especially, this has to go in a circle, right? And it is unlikely that this mass will jump around here like this, correct? That's not what happens unless you're somewhere where the tension goes to zero, then it starts to happen in a funny manner. But here, as it is hanging, there is a constraint that it has to move on a circle of length L, right? And that's the job of T. It's a T, in a sense, makes sure, or constraints. I think I want to use the word constraint because Lagrangian works a lot with that, right? So constraints M to move
Along
on
the
circle. And then we ask, oh, well, how should it, how can we make that happen? And remember that if you have a circle, the gradient of a surface of a circle, or if you have a sphere, for example, gradient of a sphere is a normal direction to that, and the normal direction is in the force of tension. Like, think of the normal force. Yeah, that's another quantity in here, right? This is a normal force, and there is a mass m that's rolling around, and there is mg acting downwards, and the normal force is acting upward, right? And let us say there is some friction for a moment, right? Let's say this is rolling, so that there is no, and if it is rolling perfectly, then there is no friction. And then we again ask, what is the role of this normal force? Can we have a normal force in an opposite, in a direction that is not perpendicular to the surface? Again, we ask, what is the job of the normal force? It is to make sure that it doesn't go into the medium, right? Mg requires it to go through, and it has to cancel that. It's there to make sure that it is constrained to move along that path, right? So in that sense, this is also a force that leads to a constraint, and force of tension is very similar. So the point is, I again did not move my camera, I suppose. Oh no, I did. Okay.
No, it's visible.
Okay, so with that point in mind, we should always, whenever we are doing a Lagrangian problem, look for a constraint, right? Especially if you are familiar with the Newtonian forces. The force of tension, force of normal force doesn't come in Lagrangian. Remember, these are not conservative forces, right? Tension, normal force, these are not conservative forces, but they lead to constraints. And the Lagrangian mechanics, what it does is that instead it gives up on these forces and instead introduces the constraint itself. So, and that's where the variables comes in. So here, our constraint is, so let's now write the constraint itself, is that it's on a circle, like L is equal to constant. Like L is equal to a constant. L is actually the length of the rope, right? That's not the way to say the position of the charge. So it is x squared plus y squared. And let's stick to 2 dimensions. Let's go by our earlier understanding that, okay, this will happen in a plane. In principle, we can put the z also there. But to make the analysis simple, let's say x squared plus y squared is always L squared. And that's it, constraint. And the moment that's there, then we think of polar coordinates, right? If we have a coordinate system where one of the coordinates is constant and the other is an angle. So it seems like Angle might be an appropriate coordinate, but it doesn't have to be. But angle is a natural coordinate in this system. So we go, so suppose I were to go back and, oh yeah, that is still visible in here. So that's your length L, that's your force of tension. So let's say this is XY. And this is constrained to move along, along the circle. So we have, now we can write X and Y in terms of L and theta. So let's, it's clear that the moment you say there is an equation that combines X and Y, that means there are not two variables in the system, there is only one, right? Because one connects to the other. So the idea is to find out what that is, and we look for polar coordinates. So we say this is X is equal to L sine theta, right? L sine theta, and Y is equal to L cosine theta, and this is minus, right? Minus L cosine theta. If we go by the standard coordinate system. Okay. And the angle here, theta, is with respect to the negative y-axis. Typically, in polar coordinates, it is with respect to the positive x-axis. So in that sense, it's slightly off. But once we have that, it is clear that what is happening, that because of this constraint, there are two variables. Apparently, there are two variables, but actually, there is only one variable. This is angle theta, right? L is fixed. So if I were to take a derivative with respect to time, this is actually only theta is changing with time. So maybe I can explicitly write that. So X as a function of time is L as a constant sine of theta as a function of time, and Y as a function of time is minus L times cosine theta as a function of time. And it's clear here that, oh, there's only one variable that's having time dependence. So it seems like it might be easier to work in terms of that angle theta. And that actually is the concept that usually, if you're really doing a brand new problem, which you have not seen before, to identify this constraint could be significantly hard. For example, if you have electrodynamics, right? Electrodynamics, remember, you have this, so we have this B, or yeah, del divergence of B has to be equal to 0, right? That's a constraint because I mean the charges are not affecting this. This is a pure constraint if you think of it as a fields itself, the X component of the magnetic field, Y component of the magnetic field, and Z component of the magnetic field, all three has to be divergence wise has to be equal to 0. And then that's an elaborate enough problem, significantly complicated. And then you have to find out, oh, what are the, how does this show in the Lagrangian and so on. So that gets immediately harder, like even though this is a relatively understood problem. So in that sense, what I meant was that to get this constraint equation could be a hard, it could be hard itself. And then next comes to identify the right coordinates and to write the Lagrangian afterwards is typically the hard part. But for classic examples, because we see so many solved problems, it seems like it is trivial. So it is important. Okay, so once we have that, we want to be able to talk about the Lagrangian. And Lagrangian, I should have pointed out earlier that that Lagrangian can be thought of as a kinetic energy minus potential energy. So maybe let me take a small digression here. So in the example that we did earlier, so the Lagrangian has this momentum. So this can be written as whatever is a derivative of the Lagrangian with velocity, that comes out to be your momentum. So that's a square of that quantity there, right? So because when you take the time derivative, this comes out clearly. So this could be your So this can be thought of as P square over 2m and minus of the potential energy. So minus your, let's say, what did we see there? So let's call it potential energy. So in general, what I mean is that the Lagrangian is equal to the kinetic energy, often we say just T minus U or V. So this is kinetic energy. Need not be half mv squared, but most of the examples that we'll do, that will be half mv squared. So this is kinetic energy. And this is potential energy. This should be taken and should not be taken very lightly, because typically we say the system tries to minimize the energy. That's not the case here. This is not energy. Energy will be kinetic energy plus potential energy. Instead, there is a difference between them. And in that sense, this should be thought of more as a free energy. There is a concept of free energy in thermodynamics, which exactly follows similar constructions. And it is more like the free energy in thermodynamics. So if you want a physical insight of that, that is the way to look for it. But be clear that that's not the energy. So our idea would be that always construct the kinetic energy and then subtract the potential energy associated with it. So since we have a simple system in gravity that we are working with, so that would mean that we have to write our kinetic energy and potential energy, which involves velocity square, right? So that means we have to get the derivative of that. So velocity square would be derivative of x with respect to time squared plus the derivative of the position with respect to the y coordinate square. And if I were to use, this is also a common quantity, the time derivative, since it will come so often, will be used to, we'll use the letter x dot to represent that. This will be dx by dt. X depends only on one coordinate, that's the time, so it doesn't matter whether it is partial derivative or total derivative in there. So that's a notation. So let me use that just to make you familiar. I try not to use too much notation. So that's x dot square plus y dot square. The time derivative of x, as only time dependence is in the angle theta. So that's equal to L times cosine theta. But then you have to do the chain rule and get the theta dot, right? So this is theta dot times cosine theta square plus minus L, but the derivative of cosine is a minus sign, so this is L times theta dot times sine of theta, the whole square. Again, theta is a function of time. In fact, theta dot is also a function of time. The derivative of the angular velocity is also a function of time. There is a cosine square theta here, and there is a sine square theta here. The coefficients are exactly the same. So this means that this will be equal to L squared times theta dot square. So it's a simplification so the kinetic energy will be half mv squared. So I just have to write multiply this by half mv. What about the potential energy? The potential energy due to gravity. So potential energy due to gravity is equal to mgh. Mg in this case mgy, right? And I have to be careful in this. So here, always when we are saying potential energy, it is with respect to a point. So let's say this is with respect to y equal to 0, right? So there's a y equal to 0. That's a axle, if you want, about which it is rotating, and the point below it will have negative potential energy. Above it will have positive potential energy. The pendulum is, at least in the initial points, it is negative. So, but that is taken care of by the definition of y. So that's equal to minus mgl cosine theta. Okay, I think that negative is there. Okay, so that's our velocity square and the potential energy. That should allow us to write the Lagrangian. So we have the Lagrangian would be equal to half mv squared. That's a kinetic energy. So it's just one mass and minus of mg y. That's a potential energy. And that is equal to half ml square theta dot square and minus mg mgy is, so this is plus now, I suppose. I hope I got that correct. Okay, so what's our Lagrangian again? In terms of the explicit variables, there is an angle that's dependent on time. That's your dynamical variable. There is a theta dot, which is a function of time. And there is an explicit, if there is an explicit time dependence, that's what it is. And in our case, in this particular example, this doesn't come in, right? There is no explicit time dependence. So that's half m l squared theta dot squared plus mg l cosine theta. What's our canonical momentum? So P, often you would say this is the momentum with respect to the variable theta. So that's equal to the derivative of the Lagrangian with respect to partial derivative of the Lagrangian with respect to theta dot. So that's equal to m l squared, and that is a theta dot. That's your angular momentum, if you want, if you were to think of it from the old classical or standard definitions. There is no derivative here. There is no theta dot expression there, so that doesn't contribute in there. We also need dl by d theta, which gets contribution only from the second term, and cosine theta gives you a minus sine theta, so it's minus mg l sine theta. Right, that's your two partial derivatives, and then we can get to the Euler-Lagrange equation. Euler-Lagrange equation tells us that time derivative of the canonical momentum, oops, theta dot is equal to L by d theta. In this case, the variable is theta. That's the dynamical variable. So we have time derivative of m l squared theta dot is equal to minus mg l sine theta. And that's immediately, that's of course cancellations in here. If you want, this can be written as, let's cancel m and n. This is second derivative of theta with respect to time is equal to minus g over L times sine theta. It's common to define the time period of this problem, or the angular frequency of this problem as, so you define g over L that way, and then this is if you make a small angle approximation in this, so if theta was small, like if theta was very much less than 1, but whenever you say something is small, you have to specify with respect to what? It is with respect to 1. In this sense, it is 1 radians, 1 radian. That will be very much less. And what does it mean by very much less? That's a percentage error. If you just set theta equal to 1, then you're probably making about 20% error. So 1 radian is, remember, about 57 degrees. So theta has to be small compared. So if you had exactly half 57 degrees, if you calculate, it's about 10 to 20, between 5 to 20% error. And if you decrease it, then you can reduce the error significantly. But that leads to a simple equation then, minus omega squared. Notice that this is not an easy equation to solve, but one can write the solution in terms of elliptic integrals, but this is simple sine and cosine functions. Notice that going from this step to this step, this is called a small angle approximation. And in this case, the motivation is clear, it is solvable, and we will do this in general whenever we are doing a complicated problem. Often you will come across equations of motions which are just not doable, like you won't be able to solve them. But if you were to make a small angle approximation, especially in a complicated system, like as simple as a double pendulum, right? If you have a double pendulum and that's not solvable, or it is just non-linear in many ways. But if you can get simple solutions around that, that's significantly nice. So we will use this almost as a tool all the time and try to talk about small angle approximation in general. And this is called the mode. If it is only one angle or one parameter involved here, or one dynamical variable involved here, there is only one mode. So a pendulum cannot do much. It just oscillates with one frequency. There is nothing else that it can do. But you can immediately think, suppose there were two pendulums and they were coupled to each other. And is that the only mode? So there will be one mode associated with one parameter or one angle. There will be another mode associated with another angle. And one can imagine what would be the combined system. And there will be a whole linear combination of them that is possible. And that is completely chosen by the initial condition. So even though in this example, the small angle approximation seems to be very irrelevant or almost trivial, we will see some richness in that in the examples that we will construct later on. So there will be a whole topic we will do on small angle approximation and the associated modes, right? There's only one mode here. There will be more number of modes, and the idea would be to find the principal modes associated with them. So we'll do that very quickly. So I will stop here. I'll do some more examples and connect it with small angle approximation very soon. But in your homework, I think you do more than one variables in this case. And wherever it is, start with the coordinates, look for the constraints if there are any. Sometimes there are no constraints, that you have to live with that. And once you have your coordinates, get the velocity variables. Usually there are simplifications, mostly because of the trigonometric identities. There are significant simplifications that happen. And then use the Euler-Lagrange equation to get your equations of motion. The three problems in your homework are mostly related to that. And do some simple, nice examples related to pendulum itself in the next class. We'll talk about what is the inverted pendulum a little bit, and then do more examples on small angle approximations. And I'll stop here. Thank you. Any comments or questions?
No, it's all right.
Okay, good. Yeah. Okay, hopefully this was helpful. Yeah.
Well, I'll see you.
Okay, bye-bye. For sure. Yeah. Can questions or comments?
Can you hear me?
Yeah, okay, yeah.
You can hear me now?
Yes, yes.
Okay, sorry, I couldn't, for some reason it wasn't working when I was talking. But yeah, I do have a quick question.
Yes.
If you replace the string with like a spring,
Oh,
could you get two different modes then?
yes, you will probably get more modes than that. I mean, it will not just be one mode type. First of all, you have to get the equation. Let's see. I can try to. I don't know the answer offhand, but surely more modes. Not, it won't be one. And let's see. So in this case, L is a parameter now, right? L is dynamical,
Yes.
correct? And you will have, so there will be more terms in here. And I'm wondering what's the right way to proceed there.
I mean, yeah, I can always like attempt it later.
I think to do it here will be hard. I cannot see it right away. But to answer your question, yes, I mean, I strongly feel there will be more than one mode. So there will be a combination of them. It will be interesting how do these modes combine in principle, right? When we are doing that, maybe that's a good example to try. Okay, I will, if time permits, I'll try to come prepared with that. Otherwise, we should always discuss this outside the class. If I'm not able to do that in the class, so contact me outside the class, then we can work this out, at least attempt on it, and then I can suggest what you can do, and then you can probably do more work on it. Yeah. Again, it's
Okay.
up to you if you're interested. Yeah.
Yeah, for sure. Yeah, we can discuss it later.
Yeah, it's a good question. Yes, simple answer is yes. There will be more modes. Yeah.
I see.
I strongly expect that to be more modes, but then it's not very obvious of how does the modes combine. Right? So it's
Yeah.
not, I don't have any more physical insight than probably you have at that stage. Yeah, unless I write down something, I won't get anything. So
Sure.
maybe we
Yeah.
write down the equations.
Yeah, I was just trying to think of more ways that you could have more dynamic variables besides just adding another theta. But yeah, okay. Well, thank you so much, Dr. Suchesh.
Yeah, good. Yeah.